the answers, but definitely no solution process. So we do this one by one. So for the first one, 1.5. So here you can see for whatever the orbit, it provides two pieces of information. One is A, one is E. So from our tables, we summarize, as long as we have any two pieces of information, we can always have the right quantity. So now is a good time for you to bring up that kind of these tables, and then we simply map in to see what kind of information we're asking for. Okay, so first one, we're looking for the RA and RP, the perigee distance. So this is the elliptic orbit and two foci, and this is the occupied foci. For example, this is the center of the Earth. Okay, the sat is here. Once you determine the occupied focus, then from here to here, from the occupied focus to the closest point, this is called the RP. RP called the perigee distance or perigee radius. And from here to here, that's called the RA and apogee distance or apogee radius there. So from here we have RP, because here we are given A equal to 30 times 10 to the 6 feet, and E equal to 0.2. So from here we can calculate again, pull up the tables, and here let me directly copy from the tables 1 minus E. Okay. So from here that is 24 times 10 to the 6 feet, and I equal to A, again 1 plus E, and that one equal to 28 RA 36. Okay. And the second one is we want to find the specific energy of this orbit. So here we write it up, the specific energy equal to V squared divided by 2 minus mu over 2A, mu over R. Okay. For this one, you need information of the R and velocity V. But at this moment, we don't have such things, because here we need two parameters. On the other side, thinking is the specific energy can be written by mu divided by 2A. One is 2A, and we do have a 2A. So once we add it up, from the apogee to perigee, that is a distance 2A. So simply 2A equal to I plus RP. So we go to these directions. This option will be easier. Okay. So that one will be equal to. So from here, right now we are in the English unit. So check into the Appendix A of our textbook and pick up whatever the unit for the feet. So that one, sorry, I forgot. I forgot the minus here, so that should be minus. Energy for elliptic should be minus. Okay, so here minus. So nu for that one is 1.40 765 times 10 to the 16. I believe it is a feet second square. And 2A simply is 60. So this one is minus 2.36. And now we find the semi-lattice rectum or the parameters. So that is the word I forgot. Semi-lattice rectum, that is another name for P. Okay. So basically here we want to find P. And P, again, we can check out from the tables here. P equal to A times 1 minus E squared. And what is A? A simply equal to A equal to RP plus RA divided by 2. Okay, so we plug in here, then we can calculate P, point A. Again, what is P? The P, if you really want to label it on the graph, the P is from the occupied focus. If you draw it a line vertical to the perigee distance from here, that is P. Okay, my drawing is not so perfect, but the smallest radius should be RP. Elsewhere, all the radii at elsewhere should be greater than RP. So that's a P. The last one, and find the length of the position of the vectors at the true anomaly. Sometimes I do need to stop and to interpret what I mean written in English. And basically, it's this: we want to find the value of the R, the magnitude of R, at the position and the true anomaly equal to 135. So here is this. At these positions, and we want to find this R, and this angle is 135. So that is the meaning of this. Simply for this case, we simply want to find R value at nu equal to 135 degrees. I think that is statement of the problem. So from here, naturally, we can see that kind of provide us a hint. We simply utilize the equation of the orbit, right? For this one, nu equal to 135 degrees. And now we calculate P already. We have E given, so this one should be done very easily. That one equal to 3.354 times 10 to the 7 feet. Okay. So that is for the problem 5. And we'll move on here. So for the next one, find equation of the velocity. Find an equation for the velocity of satellites as a function of the total spread energy distance from the center of the Earth. Okay. Are we okay? Let me erase this portion. We start from here, 1.6. And here we have velocity and related to positions. And simply this one, we use this one. We have to rewrite, so V square equal to 2E plus mu over R. So therefore V equal to the square root of 2E plus mu over R. So for this question, we are given specific energy, and we are given R, the functions, we are given the distance. So here is the velocity. So that is, this one is pretty straightforward. Okay. The next one, 1.9. So for 1.9, again, this imply is elliptic orbit. So before we decipher the statement, let me draw this one here. So this is the occupied focus, which means the center of the Earth. And right now we are given, we do this one by one. That is the flight path angle minus 60. So this is R, and moving in that directions and moving. And you see, I picked this point to draw these situations because here you can see it has a flight path angle minus 60. So again, if you remember in one section, when I remember we talked about that one, if satellite is moving in that direction, basically in the upper portions of the orbit, all the flight path angle is positive, and the lower portion is negative. So I pick at these locations. Okay. So from here, R is given there, and then flight path angle is given. By the way, the other this is Earth. Okay. The other way you can justify a negative flight path angle is this. Locally, if you would see that space object is moving toward this space, the surface of the Earth, then that flight path angle is negative. So from here you can see if you are the small persons and you're sitting on the surface here, so that is a hand, that is your feet. Okay, from here you can see this one basically is kind of falling. You would have a feeling this one is falling toward you on the surface. So definitely that is the negative flight path angle. If you feel something that is moving away from the surface where you are, then that is a positive flight path angle. So there's a two ways provided to you. Okay, so from here you can see the magnitude here is 60 minus 60. Let me focus on the magnitude only. Okay. So that, yeah, there's a 60. So from here we can say, so this is the R1. Okay, so that is R1 here. And it has the, this space vehicle, this statement saying that the space vehicle enters the atmosphere of the Earth. So basically that's saying at that position, the space vehicle is at this altitude above the Earth's surface. So from here we can determine R1. So R1 is this location from the locus, from the focus to where it is. So basically that is altitude plus the radius of the Earth. Radius of the Earth plus 300,000 feet. Okay, so this one, let me convert it into the DU. So that is 1.014336. The radius of the Earth. Okay, the DU, that means I use radius of the Earth as the 1 DU. And also velocity at this position, this is position 1, so that is the V1 here. We are given is there, so 25000 per second. And now at the second positions here is, this is second position, this is one position, two positions. At the second position, it has the altitude 100 the mm. So here we can say R2 equal to the radius of the Earth plus 100 nautical miles. So again, that's a different unit. We can convert it into the DU. So that is 0.290053 DU. Okay. And we want to determine the velocity and flight path angle. So here we simply want to determine, let me highlight here. So things gradually come to here. So we want to determine what is V2. And also we want to determine what is the flat path angle here. Okay, so that's kind of the virtually using graphical, we determine we're looking for the two pieces. So right now we can determine velocity v2 first. How come we can do it? Simply we can utilize this equation here. The energy equal to v squared over 2 minus mu over r. We use these equations and plug in at point 1. At point 1, we know the r, we know the v, so we can calculate the energy. So I simply plug in is v1 squared and mu over r1. Okay, v1 and r1 we plug in from here. And again, I use the different units, so hopefully this one will be really patient from you, convert all the units to the same thing. Okay, but anyhow, the concept is this one. So right now, again, from at R2, at point 2, so that means here we have R2 given. So from here, we should be able to calculate V2. So V2 can be determined. So probably I would say, how about this? We do a little bit of exercise. So V1 we convert it into the DU/TU. Okay, that one again, check using the tables, using the appendix A, and that is 0.9639. Okay. So everything we put in here, so the V2 will be 0.949207 and DU. And that one, again, if you want to convert it, that is 24618.9 foot per second. Okay, so we have this one done. Now, remaining how to determine the flight path angle. Any strategy? Here you can see up to now from chapter 1, we have quite a bit information from on one side is about the orbit. From the orbit, we have the equation of the orbit, and we have the flight path angle information. We have angular momentum. Okay. On the other side, you think about in terms of the geometry, we have conic sections. From the conic sections, we have the tables we summarize, right? In their table, there's plenty of information. And also from the table in specific, you can relate P as the distance we parameter connecting to the angular momentum. So from here, once you want to study the flight path angle, the hint is this. The flight path angle is always related to the angular momentum. So if you remember, the angular momentum magnitude, the angular momentum is R cross V, or the magnitude is RV times cosine phi. Phi is our flight path angle, right? So that kind of help you to think about this one. So therefore, because angular momentum is conservative, we have R, we have V. RV on 2 point R radius. So here we simply base upon this one. So that means R1 V1 cosine V1 should be equal to R1 R2 V2 cosine V2. So we check out this one. So R1 V1, we know this, and V1 is minus 60 we are given. R2 just been here and the V2 just been calculated. So here we can calculate V2 easily. Okay. And once you calculate, please pay attention because here you're going to take the arc cosine. When you take the arc cosine and you have to know which range, which number you pick up. But if you know that one is precisely, that one is minus 59.96 degrees. Okay. that is for this one, and then 17. For 17, we want to show the speed of a satellite on the elliptic orbit. Share with you my experience. I won't at one time to read through all the statements. I will read piece by piece and graphically draw something and to map the information. So here's 17. So that is the elliptic orbit, and this is the occupied focus. Okay, we have an elliptic orbit. The speed of the satellite at the end of the major axis. So this is the major axis. This is the minor axis. At the end of the minor axis is here or here. Okay. For this one, is asking to see, want to calculate the speed over there, and simply here it involves two kind of orbits. The first one, it asks us to calculate this velocity, the speed here. So let me say this is speed, okay? And we want to see this speed is equal to that speed on the same circular orbit at the same location. So here, this is the radius of the circular orbit. So that circular orbit, let me draw in this way. Okay, so here we want to know whether the two expressions of the velocity is equal or not. So that's the statement of this problem. Okay? So we can do this one. So for the green one, so V and the ellipse basically is equal to, again, we can utilize these equations. E equal to V squared over 2 minus mu over R, and so say, assuming just for arbitrary, let me say this is the A. Okay, so that means the V equal to 2E plus 2 mu over R. Okay. So using these equations, and here from ellipse, we know this is C. C is from the center to the focus, and B is the semi-minor distance. So basically, this side is the equal to square root of B squared plus C squared. So this one is exactly equal to A. Okay, so at these locations, and also with using the information R equal to A. Okay? So we plug in here, so that is equal to mu over A. So after the arrangement, you should be able to see this one quickly. Here, this one is minus mu over 2A. Okay, so let me rearrange. So this one is on the other side, for the circular orbit, for the circular orbits, we know earlier from the start of today's sections, that is mu divided by radius A by radius R. So for this case, the radius of the circular orbit is exactly equal to A. So that is mu over A. So that's it. So basically these objects at that particular location, they have the same speed. Okay. The next one show that the object is located again. 1.18. Okay, anyhow, I spot here, I didn't spend time to do this one, to understand this one in detail, but I spot that the semi-minors, and then, so basically that indicate to me is the elliptic orbit again. So that is the occupied focus. So located at the intersections of the semi-major, semi-minor axis, so basically the same thing. So this is the semi-major focus, semi-minor. So it's saying here intersection of the semi-minor axis here or here. So right now concerned at the same location like we did here. So for this one we determine locations, then we want to express that expression. So here, this is the satellite. So here, let me say this is the true anomaly nu. Okay. So from here, we want to know is this the orbit can be described by this. And at these particular locations, R equal to A. Okay, the same analysis as we have here. And so assuming this one has an eccentricity E, then we know the P equal to A times 1 minus E squared. Okay, and at this location R equal to A, so at point 1, we have is R equal to A, and so therefore A equal to R equal to A and P equal to A times 1 minus E squared, and here is 1 plus E, and cosine nu. So therefore from here we can have a little arrangement. So that means we cancel with scale A from the both sides of this one. So 1 plus E cosine nu equal to 1 minus E squared. So therefore we cancel 1 out, and so therefore you can see basically E cosine nu equal to minus E. Is that what we're looking for? Yes. So here is a little minus there. Okay. So this one provides us another quick calculation of the, say, true anomaly. So yeah, either way. Okay. So that is for this exercise, and